Now coming to question number 7, one tricky question. It says f be a polynomial with integer coefficients. Define a1 is equal to f naught, a2 is equal to f of a1 is equal to f of f naught, and an is equal to f of an minus 1 for n greater than or equal to 3. If there exists a natural number k greater than or equal to 3 such that ak is equal to 0, then prove that either a1 is equal to 0 or a2 is equal to 0. This question is from one of the prestigious exam we call as Putnam from its previous year. You can check the data is slightly changed, some variables are some changed, you can see what exactly difference is. But here what you can see, suppose I take a1 is equal to 0, although let me make it very much clear that we have to start with ak equal to 0, then we have to prove either a1 will be 0 or a2 will be 0. But just a scenario, if a1 is equal to 0, then you can check a2, which is f of a1, will be f of 0, and f of 0 is a1, but it is 0. So you can see all these a1, a2, this way if I do, all these numbers will be 0, so ak will also be 0. So there is a scenario that if a1 is 0, ak will be 0, or you can say that ak can be 0 in one of the scenario when a1 is 0. But let us now focus on whether ak is equal to 0 implies a2 equal to 0 or not. Okay, now to do this thing, what I am going to do here, that suppose we are given ak is equal to 0, then f of ak will be equal to ak plus 1 from this definition. And because ak is 0, so this f0 will be equal to ak plus 1, but f0 is a1, so this ak plus 1 becomes equal to a1. So that is one thing. Now similar to this, if I apply once again, f of ak plus 1 will be ak plus 2. Okay, and because ak plus 1 is a1, so this f of a1 will be equal to ak plus 2, and f of a1 is a2, so we have proved from this thing that f of a of k plus 2 is equal to a of 2. So these two things we have proved. Tricky question, but let us do it step by step. My next step here would be, first I will prove that because this function f is with all integer coefficients. Okay, so this a1 is just f0, that is the constant term, so it will be integer. Now a2, which is the value of this polynomial at a1, that is integer with integer coefficients, so this will also be integer. So this way I can say a3 is also integer, and so on. All these a1, a2 up to an, they all will be integer. Now what is the implication of this thing? If a1, a2, they all are integer, and I write an minus 1, okay, then this means it will be f of an minus 1 minus f of an minus 2. Okay, now if I take f function to be a polynomial of capital N degree, let me write this function also here. Fx is equal to b capital N into x power capital N plus bn minus 1 x power n minus 1, and so on and so on, plus b1 x plus b0. Okay, so here you can see this f of an minus 1 minus f of an minus 2, if I do, I can take b capital N common, and here an minus 1 power capital N minus an minus 2 power capital N. Similarly, next term would be b capital N, and here an minus 1 once again, but power will be capital N minus 1 minus an minus 2 here, capital N minus 2, and power will be capital N minus 1. Let me correct it. And so on and so on. The last one would be b1 into an minus 1 minus an minus 2. So what you can notice here, all these terms are such that you can take an minus 1. Let me write in the next step that what we can see, that this an minus 1 can be written as, in all these brackets I can take an minus 1 minus an minus 2 common, and whatever is remaining, you can see because they all are integers, I can write this as integer. Okay, so this concludes one very important thing here, that an minus 1 minus an minus 2 will be dividing an minus 1. Okay, one lesser subscript you can see will be dividing one upper subscript. So I can say this using same thing, that a1 minus 0 will also be dividing a2 minus a1. It can be proved similarly, or you can think of a1 was f0 and you can say a0 is 0. You can take that way also, and then you will be able to prove that a1 minus 0 divides a2 minus a1, and this will divide a3 minus a2 and so on. Okay, and we will be getting ak minus 1, and then we will be getting ak plus 1 minus ak and so on. So you can see this a1, let me use this space here, a1 divides a2 minus a1 and so on. After skipping few terms, what you can see, this ak plus 1, as you can see, I proved it was a1, and ak we are given as 0, so this divides a1 here. This becomes a1, sorry, this becomes a1. So a1 divides a2 minus a1, and a2 divides this, and this divides next, and so on, and this term here is becoming only a1. So what you can say now, that a1 divides a2 minus a1 and this divides a1, I think that is only possible if my a2 minus a1 is equal to either a1 or minus a1. Not only a2 minus a1, all these terms that are lying in between, they will also be like this, a3 minus a2, ak minus 1, they all will be either a1 or minus a1 and so on. I will write till ak minus 1. Now, if I add all these terms, a1 minus 0 plus a2 minus a1 and so on till ak minus 1, you can check it is becoming kind of Vn method. So a1 will be cancelled, then a2 will be cancelled, only ak will remain, but that too is 0 because we are given in the question. So sum of all these terms are 0 and each term is either a1 or minus a1 as I claimed by this logic. Okay, so some of them will be plus a1, some of them will be minus a1. Okay, that means there will be some terms, you can say two consecutive terms, out of which one of them will be a1 and other will be minus a1. What I'm claiming, that some of them will be a1, some of them will be minus a1. Okay, so there will be, if I call this as first term, I call this as second term, and I call this as kth term. So among these 1, 2, 3 up to kth term, there will be two consecutive terms. One of them would be a1 and one of them would be minus a1. So I can say that sum, let me call that as am minus 1, and then am minus 1 minus am minus 2, or maybe I can use the next one. So I will be saying am plus 1 here and am here. So am gets cancelled and we are getting am plus 1, and this will be 0 because one of them is a1 and another of them is minus a1. So am plus 1 is equal to am minus 1. So this is what we have got here. Okay, let me use next slide. So we proved that am plus 1 is equal to am minus 1. Now, if I take the value of this polynomial over these numbers, so this will be like this. So here we will get am plus 2 is equal to AM. Now if I keep on doing this way, I think this AM was in between here. Okay, so we will be getting AK to be equal to AK minus 2, and then AK plus 1 to be equal to AK minus 1, and ultimately this is what we are looking for. AK plus 2 is equal to A, that will be equal to AK. Yeah, AK. And we proved in our this first slide that AK plus 2 is A2, and AK we started with 0. So you can see A2 is coming out to be 0 here. Okay, I think for A1 we may not be able to conclude whether it will be 0 or not, but yes, for A2 will definitely be 0. But yes, if A1 is 0, then also AK will be 0. So there will be mixed kind of scenario. You can say that A1 0, then also AK 0, and some cases when A2 is 0, then also AK will be 0. In fact, when A1 was 0,